Good afternoon, everyone. Thank you for joining today's session at IEEE Wireless Communication and Networking Conference. My name is Mo Keshani from the Electrical and Computing Engineering Department from Iowa State. Today, I'll be discussing our advancement in utilizing Bluetooth Low Energy, or BLE, for enhancing security in wireless body area network, highlighting our newly developed dataset and its implication for healthcare technologies. Wireless body area networks, or WBANs, are the forefront of integrating technology with human health monitoring. These networks typically consist of various sensors attached on or inside the human body that monitor different physiological parameters and transmit data using Bluetooth Low Energy technology. BLE's low power consumption and efficient data transmission are crucial for devices that are critical to patient health and required long battery life. For example, the image on the right side shows a tooth-mounted sensor that measures the pH of saliva and uses BLE to transfer its measurements. However, security is critical, especially in healthcare applications. BLE addresses security through several authentication mechanisms designed to prevent man-in-the-middle attack, including numeric comparison, passkey entry, and out-of-bound, often implemented with NFC. These methods ensure that the devices communicating are the ones they claim to be, thereby safeguarding data integrity. The accompanying images illustrates part of the pairing process between a phone and a smartwatch using BLE, where the watch displays a number that the user must input into the phone to verify the authenticity of both devices. Implementing these security measures in real-world scenario possess several challenges. Many health monitoring devices are constrained by their small form factor and lack of sophisticated input and display interfaces, which complicates user interaction required for secure pairing process. Additionally, the limited energy capacity of these devices make maintaining continuous security measures a challenging task. To address these challenges, we explore physical layer security by fingerprinting the physical layer signals of BLE devices. These techniques involve extracting the unique characteristics from hardware and transmission channels, which are inherently difficult to replicate or tamper with. This not only bolsters security but also aids the reliable identification and authentication of device within the WBAN. Additionally, in the blue band configuration, the body significantly affects the transmitted signal, a crucial aspect that has previously received a little attention. Our project led the creation of comprehensive BLE RF datasets for machine learning applications in blue band. This dataset is unique for several reasons. First, dual recordings environments. It includes both on-body and off-body recordings. The on-body setup simulates typical use case of wearable healthcare devices, while off-body setup accounts for external devices within proximity but not directly attached to the body. We utilize two USRP X310 software-defined radios capable of capturing the entire BLE spectrum. These radios are highly sensitive and precise, ensuring that the data captured is of high quality and utility. Controlled conditions. All recordings were conducted inside an anechoic chamber to eliminate external RF interfaces, interferences, and maintain consistent environmental conditions. This setup allows us to accurately benchmark BLE performance and their interaction. For on-body recording, we strategically placed 12 BLE devices on various body parts, such as the arm, chest, head, torso, and wrist. The diversity in device location allows us to analyze how the human body affects RF signal, which is crucial for applications in healthcare monitoring where sensor placement can vary significantly between patients. Furthermore, we employed two receiving antennas located on the left and the right side of the hip to capture the RF signals. This dual antenna setup helps us in studying the signal propagation and variation as the body moves, providing data for both the static and dynamic states. Understanding these variations is vital for developing algorithms that can accurately intercept sensor data under different user conditions. Turning our focus to the off-body recordings, we extended our setup to include 13 BLE devices positioned in 7 distinct positions, as shown in the image on the right. These positions were chosen to be above half the wavelength apart, so that every position experiences a unique independent channel. Moreover, we varied the transmission power levels of these devices between two settings, low and high power. This variation helps us understanding the impact of amplifying hardware, and the signal-to-noise ratio for the fingerprinting process. We also used two antennas about 50 centimeters away to test the robustness of signal receptions across different scenarios of the WBAN dataset. Overall, this dataset consists of the on-body and off-body setup, with each one recorded with two different SDRs, and each SDR records the signal through two channels simultaneously. For on-body, each antenna was swapped on the left and right side of the hip, and there were 12 different devices for when the body was static and moving. Now let's look at the traffic generation. In generating traffic for this dataset, we employed a server-client connection to mimic typical network traffic seen in the BLE transmission. This setup includes a BLE device acting as a central server node which collects and processes the data. The server sends an advertising packet every advertising interval. In between, the client sends a packet every connection event interval, and the server, based on the configuration, will respond to that request. This client request is shown in green, and the server response is shown in yellow. The graph at the bottom shows the actual server client data that was recorded. For example, frame 0 is a client request at the channel 29, and frame 1 is the server response at channel 29. Frame 4, 5, 6 are the advertisement frames. For data acquisition, we used one specific node as a server, which was the same for both on and off body experiment. We also made sure that in every recording, only one node client is transmitting, reducing the uncertainty of correlating the recordings to the nodes and avoiding interference. Moreover, we implemented RSS thresholding to capture only meaningful signals, reducing noise and storage size. After the RSS thresholding, the raw recording files were saved, which are accessible on IEEE data port. To remove the server frames from the raw file, we developed an algorithm to separate the client and the server frames. Then, client frames are stored in a MongoDB database, a flexible and scalable storage solution that supports complex queries and large datasets. This setup not only facilitates efficient data management, but also allows for dynamic data analysis and real-time processing, which are essential for developing responsive WBAN systems. Let's summarize the characteristics of our datasets. The data has been meticulously compiled to ensure comprehensive coverage of scenarios relevant to the BLE-based wireless body area network. Here are the key features. The dataset includes approximately 10 gigabytes of on-body and 40 gigabytes of off-body data. This extensive collection comprises of over 12,000 samples of on-body recordings and 80,000 off-body recordings captured across various setups and conditions. For practical engagement, we have prepared a Google Colab notebook, which serves as a live example to demonstrate how to query and manipulate the dataset. This interactive notebook includes Python scripts that interface directly with the dataset, enabling users to perform preliminary analysis, visualize data trends, and even run machine learning models directly within the browser. But as an example, the image shows a simple query from on-body portion of the dataset where it selects all the recordings of the right chest node while the body is stationary. This specific query will return 518 recordings. Diving deeper into the analytic capabilities enabled by our datasets, let's explore the specific features captured within it. Each recording in the dataset includes BLE channel number, frame length, RSSI value, and additionally the maximum and minimum of the frequency deviation as shown in the image below. Each symbol represents one bit, where the plus 250 kHz deviation indicates a 1 and a negative 250 kHz indicates a 0 of the data stream. The dataset supports various analysis from basic signal strength evaluation to complex machine learning based classification. One of the pivotal applications of this dataset has been on-body node classification. These models are essential for distinguishing between signal originating from different type of the devices and different body locations. We utilize various machine learning algorithms, including decision trees, support vector machines, and neural networks, to classify on-body nodes based on their signal characteristics. The model were trained using portion of the datasets with rigorous cross-validation to ensure their accuracy and robustness. We were able to achieve about 84% accuracy for a static condition of the body and 74% accuracy for when the body was moving. Let's now look at the practical application and the prospective future advancement we envision with this dataset. Our work does not just end with the data collection and analysis. It serves as a foundational step towards a broader impact on wireless body area network. Authentication. Using signal characteristics to enhance device authentication process, thereby ensuring the data transmission and security and privacy. Ranging localization. Leveraging signal strength and propagation data to improve the accuracy of device localization within a WBAN, which is crucial for emergency medical responses. Physical layer security enhancement. Physical layer security enhancement. Implementing advanced cryptographic measures that are tailored for the unique aspects of the physical layer communication in WBANs. Future directions. Expanding dataset application. We plan to include more diverse environmental scenarios and more complex device interaction to simulate real-world conditions more accurately. Improve data collection methodologies. Innovating beyond current data collection methods to include real-time data, streaming, and analysis capabilities. Integrate more complex machine learning models. Exploring deep learning and reinforcement learning models to predict system failures, detect anomalies, and automate network management tasks more effectively. To summarize today's presentation, let's recap the pivotal points. Importance of physical layer security. We emphasize the necessity of enhancing security at the physical layer to prevent unauthorized access and ensure data integrity within WBANs. Introduction to the BlueBand dataset. We introduced a comprehensive dataset designed to foster research and development in WBAN security. This dataset is distinguished by its dual focus on on-body and off-body recordings, detailed signal characteristics, and high-resolution data collection. Utility of the dataset. The dataset is not only a tool for academic research, but also a practical resource for developing advanced security protocols and improving device authentication and localization techniques. Demonstration of machine learning potentials. We showcased how machine learning could be harnessed to enhance the classification accuracy of on-body nodes. In a sense, our WBAN dataset is a catalyst for innovation driving forward both theoretical research and practical application in the rapidly evolving domain of wireless healthcare monitoring. In closing, I would like to thank you all for your attention and interest in our work. I look forward to your questions and a fruitful discussion about the future of wireless body area networks and how we can collectively enhance their impact in healthcare. Thank you.